My name is Les Wicker, and this is the second of our programs that we're going to do, and the title of our programs are Three Things You Must Understand. And we talked last time about, just to kind of recap a few things of what we began to do, was we said that we're going to consider the workings of one eye in relation to the ideas of evolution and creation, and what makes sense when we consider the complexity that we see in the universe. And you remember that if you were with us last time that I held up these beautiful peacock feathers. I really wish I had a peacock rather than just the feathers of a peacock, but at any rate, maybe someday I'll get one. But these are awesome creations here. And among these are just one, member of the pheasant family among many that are just beautiful to look at. But before I get into the content, we left a young man over here working, and he took his blindfold off, but not before he had gone through a box. And we ran out of time, but he was working on this box of rocks, and I put inside this box of rocks one arrowhead, shaped kind of like this one that I drew on the board, and so that you could get the point that someone that is even blindfolded could pick out something that had design to it, that was purposeful, and that was intended to serve a useful function in someone's life. An arrowhead in this case would have been used to shoot at perhaps a deer or some game, or even a person if they were at war. And Lindsay, stand up here. And now, he was blindfolded, and you'll just have to trust me on that because our program ran out before he actually got through all the rocks. But Lindsay did find the arrowhead. Do you have the arrowhead, Lindsay? All right. There it is. Now he found this arrowhead. Wait, let me put it against my shirt so you can see it better. He found this arrowhead with this blindfold over his eyes. So he was not even looking he could not see the arrowhead, he just felt of it. But he still, even just with this sense of feel, he was still able to discern design when he came across it with his fingers. Now, this is good. I mean, you could discern that. And the point we're trying to make here is that if it takes intellect and purpose and will and design to create and skill and dedication and all those kinds of things to create an arrowhead, how much more does it require intellect and design and purpose and will in order to create something as complex as the human eye? Well, this is what we're going to talk about this time. Okay, Lindsay, thank you. You did a good job. Now, we had never done that, by the way. He had not practiced that beforehand. That was the first time he'd ever tried it, and he did it the first time, and I knew he would, because we human beings have an amazing ability that I believe is God-given to discern design, because we see it all around us. Is it simple or is it complex? That's what we want to know. Is there design intention with purpose behind it? Because non-living matter does not look for a way to improve itself. All right, let's talk about the eye. The first job of the eye is to condense and convert light waves from the outside world into electrochemical connections that make other electrochemical connections in the back of your brain, the visual cortex, and thereby produce a full color, sharp focus, moving, real-time picture inside our heads. And we know that's what it does, but how does it do it? Well, you should know that a significant portion of what happens in the visual cortex is still unknown. In this age of medical technology, we still don't know really how it works. But let's just consider the round organ itself and not get into the visual cortex at all in this program. Let's consider the round organ, and we'll go from there. Let me get this get some space up here for us to work. First of all, erase the arrowhead and the rocks. All right. Now, let's first just draw a circle. This is the orb of the eye. Now, the eye is like a ball. It's a sphere. Everything, first of all, emits light waves and must be condensed to get back into the eye. Initially, that process is begun by the cornea, which if the eyeball is pointing, let's say, this direction, the cornea is a bit of a bulge that comes off of the eye, like this. Light waves, if we were looking, let's say, at a tree, kind of like a spruce tree, this kind of thing out here, this tree and everything that we look at, it comes in and begins to be focused by the cornea. And what it does is it refracts light. It refracts the light waves that are coming in. And it bends them. It bends the light waves. So what has to happen, the reason the eye works, it has to take in this broad view and it has to condense it. It has to get it into the eye. It's much smaller than it actually is. So the cornea actually begins to refract the light. It is like the first lens of the eye. It's not the actual lens of the eye, but it is like a lens in some ways. Within the cornea itself, which is a transparent convex window to the eye, is a pressurized liquid that assists in giving the cornea this bulge that we see here. It's necessary to bend the light waves, and it's called the aqueous humor. The aqueous humor is inside of this. It's a pressurized fluid. Now the cornea, along with the whites of the eye that is exposed to bacterial invaders, is washed constantly with a specialized antibacterial fluid that is produced by special glands back behind your eye, and it's distributed across the eye involuntarily by involuntary blinking. You blink all of your waking hours, whether you realize it or not. Sometimes you do, but most of the time you don't even realize you're doing it. You're blinking, and throughout the day, and that is to keep your eye clean and keep bacterias and invaders out. The eyelashes also protect the eye. The fact that and there's an accelerated nerve response whenever any object gets close to your eye. Not to mention the fact that the whole eye is set back into a socket for protection. I'll mention too, in the interest of deciding whether this is simple or complex, purposeful design or blind chance, that within your 100 trillion or so cells, each of which contain information roughly equivalent to a public library, every single one of those 100 trillion or so, there is a microscopic, opaque, rope-like substance, generally known as collagen. Now it's opaque throughout the body, that is except for one place, where the rope-like structure changes into a matrix form and becomes perfectly transparent. Would you like to guess where that is? Well, it's in the cornea. And all the other parts of the eye would be totally useless if just the cornea, if the cornea was opaque collagen like all of the rest of the body. You see, you can't see through my hand there, but you can see through my cornea. You're seeing through my cornea. If you look in a mirror, And when you see the color of your iris, then you are seeing through the cornea to your iris. And so it's clear, it's perfectly clear, otherwise you wouldn't be able to see. Also, understand that all parts of the body need oxygen, which is carried by blood throughout the body. But there's one problem. Blood is also opaque. You can't see through it. And, well, how does the cornea get the oxygen that it needs? It doesn't. There's no blood veins going into it. Unlike all of the rest of the body, it gets the oxygen directly from the air. It's the only part of the body that does. The cornea gets the oxygen it needs directly from the air. It's not brought in through the veins and by the heart like all the rest of the parts of the body. Now, let's move on to the colored part of your eye, called the iris. Now, it can be various shades of color, which is fairly remarkable just in itself, because recognizing that the iris is actually muscle. Now, do you know where there's another, eyes can be anything from green to blue to brown to gray and various shades in between. Do you know of any other muscles in the body that are blue or green or brown? No, there aren't any. The eye is beautiful, and it contrasts beautifully with the white part of your eye. But what it do? Well, it does the same thing that the aperture in a camera does. The camera is often used as a comparison to the eye. And if we were using that analogy, the cornea would be the first lens of the camera. And I've got a camera here. Where is it? This is a kind of an old-fashioned camera these days. It's an old SLR, single lens reflex, that I have. And this is often used as a comparison to the eye, and for good reason. There's a lot of comparisons from a camera to the eye. Now, one of the things, if we were going to use the analogy of a camera and the aperture or opening, the aperture is the opening of the iris. Now, let me just show you this for a moment. I've taken the lens of this camera off of the camera itself. And if I take this, and I hope you can see this, but if I take this and I can shut this down by moving a little button back here on the back of the lens. And I'm hoping that you will be able to see that. But you see how it's closing and opening there. Now, the reason it's doing that, or the reason a camera needs to do that, and modern cameras, of course, are even more complex than this one is, but this one suffices our purposes in order to show you what it does. But what does it do? Well, when you go out into a bright daylight, like from a room, and it's very bright outside, what happens is your iris shuts down the amount of light that is coming in to your eye. And likewise, if you were coming from the outside and you came into a building and where there was not a lot of light, then your eye would open back up. You can see this kind of thing and sometimes in a cat's eyes, although a cat's eyes are elliptical and they work differently than our eyes. That's something else we'll discuss, but the difference in various creatures' eyes. But this is why it does it. But how does it do it? That's what we want to know. Have you ever thought about this? How, knowing that all muscles contract, there aren't any muscles in the body that push, or they all contract, and they generally work in pairs. I think they all work in pairs. How would you expect the muscles to be composed in order to achieve the opening up? Well, let's think about this a minute. Let's draw another picture here. Let's say this is your eye. This is the pupil here, where the light actually goes through. If you went into a dark room how would the muscles need to be arranged or composed in the iris in order to open up and get bigger? Well, they're composed in a radial form like this, so that when they contract, see they're mounted out here, and when they contract, they pull open the iris to let in more light. Now these muscles are tiny, microscopic muscles. Okay, if that's true, then how would the muscles be composed, knowing that they can't push it back and keep a perfect circle? How would the muscles of the iris be composed in order to concentrate or pull in and bring the pupil back down to a small portion to where you would need if you were going out into bright sunlight? Well, actually the way it is there is another whole set of muscles behind the radial muscles. It's like this, like the spokes of a tire. There's another whole set of muscles that are arranged in a circular pattern behind the radial pattern like this, and when they contract, they close down the pupil. And so that's how it works. Is it simple or is it complex? Now, behind the iris is the second lens of the camera. And most cameras, the eye rather. Most cameras, but I think all cameras have at least two lenses, some more. This one here has two lenses. And you can see that when I move this wheel here, that this lens, the front lens, actually moves forward and backward. Incidentally, a fish's eyes actually work this way. They actually move in and out in order to focus, just like this lens here does. But that's not the way our eyes work. Ours are more complex than that, and far more complex than this. Now, just for the side right now, do you think that this lens washed up on the beach somewhere? Do you think it came up out of the earth? Or did someone design this lens for a specific purpose and for a specific use? Well, it's obvious that it was designed, and very well designed. So, is it simple or is it complex? Now, the lens of our eyes are much more advanced than the fish's eyes. It uses the same lens and actually changes shape automatically. The lens of our eye, we've got the iris in here that controls the light, and then behind that we have the real lens of the eye, which sits right directly behind the pupil and behind the cornea, and there are tiny, tiny microscopic muscles that are attached to the edges of this all the way around. And what happens is we use the same lens. We don't have two lenses. Well, we do if you would consider the cornea a lens, but rather than our lenses having to push and pull forward and backward like this, we actually use the same lens, and in a similar way to the iris, these muscles on the outsides of the eye that go all the way around it actually pull automatically. We don't even think about it. They focus. When I focus on something up close, they work. When I'm focused on something far away from there, it just happens instantly. I don't even have to think about it. And you don't have to think about it either. As we get older, sometimes our ability to focus gets a little bit decreased, and sometimes we have to have glasses or contacts or something like that, or surgery to help us out. But this lens here is pulled, which makes it more elliptical. or less elliptical, depending, and when it relaxes, there's also another set of muscles that pull it in, similar to what the iris has, but different as well. So this is how the lens works, thicker and thinner, to see up close and to see far away and all points in between. Now, the light wave image crosses through the largest part inside the sphere of our eye. And this is, again, filled with a different kind of pressurized gel-like substance. That is, inside this large ball here, inside of our eye, what happens is the lens actually crosses the image and throws the image of that pine tree back on the retina, which is back here. A camera works identically the same way, except the retina back here would be the film, which would be back in here. So if I put this back on here, screw it back on, then we've got a very good illustration of the way the eye works. It comes in there, it flips over, and lands upside down. So the trunk of the tree would be up here, and then it would land on the retina in this fashion. Now our eyes, our brain turns the image back around, but the retina is the curved back of the eye. And it is very complex. The retina is probably the most remarkable feature of the eye. It is unbelievably complex, multi-layered back of the eye that is full of light-sensitive cells, or photoreceptors. They're called rods and cones. You probably learned this back in school. Placed in a very precise arrangement, the rods perceive black and white and gray, and the cones perceive color. Now, if I told you that there were, let's say, 300 or 3,750 rods and cones, that is all the way back in here, the rods and cones, if I said there were 3,750 of them, you'd say, well, that's a lot. Well, that's not actually what they are. If I told you there were 375,000 of them, you would say, well, that is very impressive. But that's not accurate either. There are actually about 375 million rods and cones in one eye. One eye. Now, and they're arranged in a very, very precise manner. The combination of these 375 million rods and cones enable us to see nearly unlimited subtleties of color and contrast. Now, in order to achieve sight, each one of those 375 million light cells must have a direct optic fiber that connects back to the brain. Otherwise, if there's no connection, then there's no sight. Let me get something here to illustrate this. This is actually a power supply for a computer, but we'll use it just as an illustration. If this were the eye, let's say, and each one of these little outlets here, inlets, what do we call these, Jamie?
Inlets, I guess.
Inlets, I'm not. Jamie's a lot better. He's our cameraman. He knows more things like this than I do, a whole lot more. But at any rate, these all go to a very specific place in a computer, and this is a power module that the computer has to have in order to power all the various separate functions of your computer. If we were to to disconnect, or just take scissors and cut all these lines here to the computer circuits inside, then there would be no functioning in your computer. That would end all functioning, right? Now, all of these are very precisely organized, as you can see. Now, there is nowhere near 300, there's not even 3,750 of these in this particular unit. There's nowhere near 375,000 of them. We have 375 million rods and cones. Every single one of them have to have a nerve fiber that is connected to a very specific part of the visual cortex in the back of the brain. Is it simple or is it complex? That's what we want to know. Well, I hope that you can see that it's complex. It's complex beyond your imagination. But now, listen to this for a minute. Most people think, and I thought before I began studying this particularly, that the nerve fibers came out the back, like the rods and the cones were right here, and the nerve fibers came out the back of the eye and came back to the optic nerve and went back like that. But guess what? It's not like that. It's not like that because God knew that each one of these rods and cones had to be fed by blood from the back of the retina. So what happens actually is the nerve fibers go inside and come along here. 375 million of them. Imagine that. And guess what? They're all perfectly clear. They go on the inside orb of the eye, all back to the central optic nerve, and back to the brain back here, and nobody knows what happens there. Now, do you see there's so much more to say about that, but do you see a problem, potential problem, with what this, with the vision, your area of focus landing right here where the optic nerve goes back to the visual cortex? Do you see a potential problem with that? Well, I hope you do, because there is a potential problem with that, and that is where this huge cord of a bundle of 375 million optic fibers going back into your brain, wouldn't that create a blind spot? Well, the answer is yes, it would, and it does. It does create a blind spot. But there is an ingenious design solution to this problem, and that is the fact that the optic nerve, it doesn't actually come like I illustrated it here. I knew I was going to do this, but it doesn't come straight out from the back. It is actually lowered, and the optic nerve comes out down here and goes back to the brain, so that your central focus area, where you have the best, sharpest, clearest image, has no obstructions whatsoever. And there's so much, we're going to have to resume this once again because we're almost out of time, but I hope you'll stay with us, and we'll finish up with the eye, and then we'll begin to go on to some other things. But we're about out of time, and we appreciate you listening to the program, and stay tuned or be back at the next program, and we'll talk some more. Thank you.